Hello, everybody. Thank you for joining us today. My name is Brad Odner. I'm a technical marketing manager with Keithley Instruments and Tektronix. Thanks so much for joining today. We're going to be talking about Keithley TSP, or Test Script Processor. We're going to be using a live instrument that you can see right there in front of you. And you'll be able to see my editor as I'm coding along with the instrument. So hopefully you're able to follow along today if you read the description of this post, of this video. If not, then you can always come back to this video later and follow along then. If you have any questions or problems throughout the live stream, you can use the live chat over on the right. We have engineers standing by to help you out with your questions or problems. You can look for Evan Hall, he'll be a moderator, and he'll be speaking on behalf of our engineering team. So to get started, of course, we have to at least talk a little bit about what TSP is. I'm assuming most of you, if you're joining today, are familiar with TSP, but if not, or even if you are, it's always good to get a little bit of a refresher. We like to think of test script processor as having three main parts: the processor, of course, the language, and the communication. We won't be speaking about the communication aspect much today, but that's an excellent topic. Maybe we can talk about it some other time. But we will be definitely using the processor and the language. The processor aspect of TSP is that all TSP-enabled instruments, like all 2600 SMUs that we're talking about today, have an embedded processor on the instrument itself. So that means that the instrument can execute TSP code without being connected to a computer. The language is based on Lua. It's Lua version 5.0.3. And it contains two different aspects of Lua. One is the programming language itself. So Lua is a full programming language. I think it's a little bit similar to Python, but it's not exactly. But it's very easily accessible, quick to pick up, a nice language to get started on, and very fast to script in, which is important, obviously, when you're working on a test instrument. And then there's the command set, which is custom for our instruments. Each instrument has its own command set so that you're able to actually control the instrument, like take readings, source voltages and currents, things like that. Lua also has I'll mention here too that there's a couple different ways to find help on programming in TSP besides this live stream. Besides just reaching out to Keithley for help with your instrument or using our forum. There's also a Lua users wiki, so if you have questions about more advanced Lua things that you want to be able to do with our instruments, that's a good resource to keep in the back of your mind. So when we talk about that processor, there's a couple things to know about when we talk about that processor on the instrument. And that has to do with the different ways that you can use TSP, or when we talk about using TSP, the different things that means. One is the traditional remote control aspect, so sending commands back and forth from a computer to an instrument. You're just one by one. This is how Skippy, SCPI, or standard commands for programmable instruments work. And if you program your instrument in MATLAB or Python or something like that, and you're not using the full advantages of TSP, that's how you control every other test instrument. Where TSP gets special is that you can have code sitting on the instrument with that accessible processor. So that moves on down to like level 2, where we have TSP with function calls. Maybe you put a function on the instrument, and then instead of sending all those commands one by one, you're just calling that more complex function. And then finally, there's TSP with scripting. When we talk about scripting, that means a more complete test. Or perhaps you're doing something a little bit more complex, or even having the instrument operate by itself without having a computer communicating to the instrument at all. So today, if all goes well during this live stream, we'll be doing all of these different remote control aspects to get you a little bit more comfortable with how you can use TSP to improve your own workflow. So as I mentioned, if you want to follow along, there's a couple things you'll need. These are also listed in the description of this video as well. Any Keithley 2600 series SMU. I'm going to be using a 2636B, which is a 2-channel source measure unit with ultra-low current measurements capabilities. If you have a a 2600 SMU that is a revision, or it doesn't have a letter designation after it at all, then all the things that I'm going to be talking about today should still work fine. Don't worry about that. If you have a 2400 series that has TSP, our graphical source measure units, then these commands won't quite work for those. They operate a little bit differently, so keep in mind, for following along today, you're going to want a 2600. You'll need, of course, a way to connect your PC to the instrument. The 2600s have USB LAN, GPIB, RS-232, and some devices to test on. I'm going to be using an LED and a little FET transistor that I have. If you don't have these, of course, you can just leave the connections open. That'll be fine. You just won't get interesting data back, of course. Oh, and of course, you'll need Test Script Builder installed. That's what I'm going to be using today. To write in TSP or program your instrument, you don't really need Test Script Builder. It's just a helpful tool. It's an integrated development environment, an IDE built around TSP. So it makes it a little bit easier to send commands to the instrument and code and save scripts onto the instrument, and we'll go through all those different aspects of it. But you can just use any old text editor. TSP is at its heart just a programming language, so you can program just by writing out text. You can program TSP with a pen and paper if you really want. The instrument just won't be able to read it. And of course, number 5 there, cables to connect the output of your SMU to devices. So now would be a good time to go ahead and open up Test Script Builder if you don't have it open already. If you're just now joining us, we're talking about Test Script Processor for Keithley 2600 series SMUs. We're going to be going through an introduction here of all the different aspects you need to get started with TSP. And I'll point out too now that if you miss something, you can always, in YouTube, scroll back a little bit in the video, listen to me say something again. Again, you can ask questions in the live chat over on the side. We have engineers standing by. So this is the Test Script Processor, the Test Script Builder editor. Yours may look a little bit different from mine when you first open it up. I may have closed some windows over here, but these are the key different aspects that we're interested in. Of course, right here, you'll be greeted first off with a welcome screen, which is great. If you want to get started with Test Script Builder, you can read some of the help documentation that's out there. But this is also where the main editor, where all your code will go. Down in the bottom, there's the instrument console. This is for connecting to the instrument and communicating directly with the instrument, which we will do shortly. And over on the right is the navigator, the project navigator. All these ones that are KE, and your Test Script Builder will also be populated with lots of folders. These are all factory demo projects that come populated for a number of different instruments. You see like the 2460, 2602. So these are a great place to get started. If you're not quite sure how to get started on your own application, you can start basing things off of this code. Now, what we're going to do is we're going to make our own project. So up here in the top left, you'll see this little window icon here, this little new icon. I'm going to click that. It'll open up a wizard. And we're going to make a new TSP project here. I'll just click next there. And I'm just going to call my project demo. That's fine. You can name it anything you like. And you see we have some things that the editor auto creates for us. We get a main.tsp, that's reminding us to insert some code there, and we get a demo project in the project navigator. Now, what I'm going to do is, I know this is hard to read. Don't worry, we're not going to do the whole live stream this way. I'm going to edit my display so that you can see things a little bit easier as we go forward. There we go. That should be better for all of you. So now we got our editor up here, instrument console still on the bottom there. So next step, we're going to connect to our instrument. I'm connected to my 2636 over USB. Other connection methods work though too. To open up the instrument connection, we're just going to click this little icon right here. You can hover over it. It says Open Instrument. That will open a dialog for us. You can use this drop-down to select multiple instruments. If you have multiple on your network, for example, you can see here I'm just connected straight over USB, so that's exactly what I want. You'll get a little opening resource window as the test script builder communicates with the instrument, and now we have our connection. So now we're ready to begin actually doing our coding in TSP. So let's first identify the instrument that we have. You may be familiar, if you're familiar with programming instruments at all, the *IDN callout. So let's use that first. Here we just get the simple report back of our instrument. So TSP can use a couple of these primary special keywords. There's a few of them. You can find them in the reference manual for the instrument. Things like *RST or star for resetting the instrument, or *TRG for triggering the instrument. That'll just initiate a trigger. So those are good things to keep in mind as well. You can't use these in your code, but they're useful to use in the instrument console to do things very quickly or simply reset the instrument that way. I'll point out, by the way, too, I like to code with the reference manual of the instrument open next to my code so that I can just quickly search through the whole reference manual. There is built-in help, though, to Test Script Builder. So if you go up here to the help, you can open the welcome or get the help contents here, and that'll open a separate window that just has the TSP reference material, not the full reference manual, but just the TSP reference for all the different instruments that are supported. So that's a good thing to keep in mind too if you like to search through commands. You can even download the Lua manual as well if you want to do some advanced Lua coding. Some Lua information is included with the instrument reference manual, but if you want to get a little bit more fancy, then you can get the Lua reference manual and start, really going ham on things. You may also check out here too some other little commands that we get with the instrument console. So things like clearing the console window if we don't want any of that later. We can abort execution if the instrument starts hanging up. Reset. We can send a software trigger, so that's the same thing as *TRG. And then we can manage scripts or delete a script from NVRAM, non-volatile memory, on the instrument. So that's handy, just a little quick management tool. And we'll use that later as well, just see what scripts are on the instrument. So first thing, whenever we start a new programming language, we have to do hello world. So of course, like you may expect, we can't simply do that, just typing out hello world. Instrument doesn't understand what that is. So we're going to use the classic print command and make a string of hello world. And there we go, we get the instrument typing back to us quick hello world. So the instrument, as I said, has that processor on it. It's running the code. This isn't happening, everything happening in the console here isn't happening on the computer, it's happening on the instrument itself. So because it has that processor, you can do lots of things you would expect with a programming language. So you can do some basic math. You can assign variables to things and then print out those variables. Lots of things that you'd expect from just a basic programming language. You can also do some multi-line things directly in the console if you like. A semicolon is an optional line terminator. It can be helpful if you're trying to put things in one line that you don't want to, that you just want to keep the ideas a little bit separate there. But the semicolon is an optional line terminator there. So when we start actually scripting, you won't see us putting a semicolon after everything. Now, besides just basic math, there's also some built-in libraries within the instrument to help you do some more complex math. So let's print, and we're going to use the math library, and let's take the absolute value of -3 here. And we get 3, just like we'd expect. How about that? The laws of the universe still hold firm. The math library has a couple other interesting things in there. So we can get pi if for some reason you're doing radial math with your instrument. I don't know, could be calculating phase or something like that of a signal that you're measuring. And you can even transfer that into degrees. There's lots of different capabilities that we have with the math library. Again, this is all in the instrument reference manual. Please do, if you're following along, play around with some of the other commands that you can find, or play around with some of these so you can start to get a little bit more familiar with the instrument. Now that math dot, when we see this math dot something, This means that what we're looking at is a table. Lua, if you're not familiar with it, is built on lots of tables. Pretty much everything in Lua is, or at least can be, a table. And therefore, the same thing is true for TSP. When we see this dot, we should be knowing that that is a table. So in fact, we can get that, we can know that for sure. I'm going to just print what math is, and we'll see that it's a table. The numbers and letters that come after there is a memory location. Not really super important for you for managing the instrument, except in very rare cases. But you can see that that's labeled as a table there. So let's do some other things with tables, because tables are important for working around TSP. So let's make a test table here. And I'm just going to define a new one. I'm going to use the curly brackets. And let's just make a couple items in here, close curly brackets, and now we have a test table. We can print that out, and we get that. Good. We have actually created a table. We get the memory location for it. How do we get those items back again? Let's print test table, and we'll use a square bracket to get the first index. TSP is 1 indexed, not 0. If you do an index of 0, you'll get nil back. So let's just go ahead and try that just for funsies. And we get nil. TSP, nil, means that the variable just does not exist. So, of course, if you're familiar with programming at all, different from 0, as you might know, different from false and things like that. Nil means it doesn't exist at all. Nil is also how you delete things. So if I wanted to completely delete this test table, I could set it to nil, and then the instrument will completely forget about it, no longer exists. I don't think I want to do that quite yet, though. Important with tables, too, that I want to call out is getting the length of a table. So we have this test table. How can we find out how long it is, how many items are in it? Because there's ways to append things to tables, or we can create tables of various size. And if we're doing a loop or something, we may want to know how many items are in that table. So there is a table library, and we're going to use table.getN of test table. And we see that there are 3 indexes in the test table. So that's a great way to, a good command to keep in your back pocket there. Now, let's start talking. All of this hasn't been anything specific to the instrument. This is just basically Lua backend. This is all coding straight in the TSP Lua side of the language. So let's do some things with the instrument itself. Earlier we did star IDN. So a TSP has its own methods for getting information on the instrument. One of the best ones is called local node, which is another table, local node dot, and let's print out the model number of our instrument. And we see that it is indeed a 2636B. Let's print out some other things. Print local node dot serial number, serial no. We'll do that. That's great if you're building your own test stand or something like that, and you need to verify what instrument you're talking to, of course. There's also commands for getting the line frequency. If you're building test stands that maybe will go across the world, and you want your code to work the same everywhere, then you may have to adjust to the line frequency of your instrument. May have to adjust your code to the line frequency. So you can use local node dot linefreq to get that. That's a quick one. There's also other information we can get. We can get the error queue, so we can find out how many errors there are. Error queue.count, that's a great one. As you're writing maybe a more complex program, you want to make sure that no errors have happened, because obviously if it's running unattended, you won't be able to know that. You can use error queue.count to check if there are any problems that the instrument has come across. And all of these really are not customizable, right? These are all just properties of the instrument. We wouldn't be able to change the model number by within TSP, because the instrument will always be a 2636B. But there are some that we can change. So let's try local node.description. And here we get it looks similar right now to like a star IDN. We get a manufacturer and things like that. But this is a customizable field. Customizable attribute, I should say. So let's set that to something else. And I'm just going to set it, we're going to set it to a string, and I'm going to set it to Brad's SMU. And there we go. Print, let's read that back. And we see now I've changed the model's description. This can be great if you want to say like, this is the top left instrument, this is the gate SMU, something like that. Then this can be helpful when you're trying to talk to instruments remotely and you need to just need an easy identifier for what they are, maybe easier than using the serial number, for example. Now this local node, what does local node really mean? I mean, local makes sense enough. We're talking to the local instrument. Why node? Why do we talk about node there? Well, node has to do with the TSP link functionality, which that's the communication aspect that I mentioned earlier. And we're not going to talk too much about it, but there's this TSP link .node, and you see that we're at node 1. So TSP link allows multiple instruments to talk to each other, and every time you connect an instrument onto the TSP link network, it gets its own dedicated node number. So if we do something like print node 1 dot description, we see that's the same instrument because local node is just a alias for that for node 1. The exact same code. Okay, so we've gotten a few attributes of the instrument. Now let's start talking to the instrument itself. If you're just now joining us, we're going through an introduction to Keithley TSP for the 2600 SMUs. This is my editor coding live here for you. Please do follow along. I think it'll be pretty fun and experiment as you're going along. Once again, got any questions? You can type them over in the live chat. If you need some inspiration for participation, maybe say, what do you use TSP for right now over in the chat? I'm interested to hear that, of what you have been using TSP for, or are there any capabilities that you wish you knew more about, or that you really like, that you find beneficial. Maybe other people can benefit from that, knowing that as well. So let's try setting the instrument level here. If you go to the command reference, you'll see a command like this that I just pasted in, smux.source.level_y. So those are just variables in general for TSP, or for the command reference. X is going to be either A or B. That represents the channel of the instrument you're talking to. If you only have a one-channel SMU, then it's always going to be A. There will only be an SMU A. You obviously don't have a channel B. And Y is going to be either V for voltage, I for current, and that's for sourcing. If you're measuring, then Y can also be R or P, resistance and power, since obviously those are very easily calculated from V and I, so there's some shortcuts to calculate those, have the instrument report them directly. So this is another attribute. So let's try setting this. You can tell it's an attribute because let's set it to, say, level V. And we'll set this to, say, 2 volts. And watch the display of the instrument there, and you'll be able to see the display change when I hit enter right there. Now we've set the output voltage, the level of the source voltage, to 2 volts there. So that's a very easy way to set the voltage. How would we measure something here? SMUA.measure, and we would do .V for voltage. And doesn't look like anything happened. Why not? Well, a couple things to note here. One, we didn't print this at all. We just told the instrument to measure. We didn't tell it to actually return anything. And also, something else to note is that this is now a function, not an attribute. So if I had just put an attribute there, then the instrument may return an error because it doesn't know. We didn't tell it to do anything with that attribute. But instead, what we get is this is a function. So we can tell that if we do print, and we'll do smua.measure.v, and let's just print that. Ooh, it doesn't like that. I made an error. smua.measure.v. There we go. Now the instrument's telling us that that is indeed a function. So let's actually print a measured voltage there. I'll make sure to type the command correctly now. There, now we get the voltage. Of course, we get very low because we never turned the output on. All we did was set the level of the instrument, but we didn't actually have it start outputting any voltage. And Actually, because I have that LED connected, I'm going to set it to an even lower voltage. Level V, and I'm going to set it to 0.5 volts. Now let's turn the output on. And we'll do SMUA.output on. There, you see our output turned on. Good. It looks like I'm not going to blow up that LED. I've blown up a couple LEDs while testing while testing out this live stream. So that SMUA.output on, what's up with that? That seems a little irritating to type out all the time, right? Well, that is a constant, and in this particular constant is equal to 1. Anytime you see those all caps, that means that we're operating on a constant. So we can just print that out, actually. SMUA.output on. And you see that it's equal to 1. That means that this is the exact same as typing SMUA.output on. What it allows you to do, though, is make code a little bit more readable than rather just having numbers for settings. For on and off, it's not too hard because on and off, as you may expect, are just 1 and 0. But some of the settings, you know, the constants can get, they're not as obvious as just on and off. So that can make it, using constants in your code like that, just helps you, helps make things, again, more readable. So constants also have the benefit of never changing. So for example, I can't go into here and do SMUA.output on equals 2. The instrument wouldn't let me do that. It's always going to be 1. Okay. Now, I mentioned aliasing earlier with that local node business. But an important aspect of TSP that can help make your code easier to work with is aliasing your own functions or some of the built-in functions. So for measuring, you know, we got that SMUA.measure.v, for example. That's not too easy to maybe keep on typing, or maybe you just don't like maybe you just don't like seeing SMUA.measure all the time. So let's alias that to something else. We're going to do measure this time, and we'll set measure I equal to SMUA.measure.I. Now I'm not going to put parentheses after here, even though measure.I is a function. And I'm just going to do that. Now what I've done is I've set measure I equal to that function. So now I can do measure I, and I'll print that. And it's going to be a very low current there. But now the instrument now I've just aliased SMUA.measure.I to this new function. I could have named that variable anything. It's just any variable that you may set. So how would we do this with something like voltage level? So let's try it with voltage level. We'll do V level, and we'll say SMUA.source.level V. Let's try that. What happens there? Have we made a new attribute or a new function? No. We have instead just set it to 0.5. So this isn't a function or anything. We've just assigned V level to the value of 0.5, the same level that level V was set to. There is a way to alias these things, a pretty quick way. Let's say we do make a variable called a source, and let's set that to SMUA.source. Now we can do a source.level V equals, let's set it to 1. See if that LED has started to light up at all. Not too much. So that's one way to do it. There's an even better way, and there's called getters and setters. I'll write that out up here. Getters and setters. These are only really beneficial if you're going to be using a attribute a lot, like you're changing voltages all the time and you want your code to run quickly. Then you can use, say, a setter as a way to set that voltage. What getters and setters do is they turn attributes into functions. So attributes are like a property of the instrument or some aspect of the instrument, or even your code, whereas functions actually accomplish something. So that's why we're going to turn an attribute into a setter, because then the action that we're going to be doing with that function is setting. And as you might expect, there's one for getting as well. So let's turn that voltage control into a setter. into a new function. So we're going to use the command make setter, smua.source. And then it's a little bit of a weird notation. There's that smua.source again, but then we're going to put a string here for level v. That's the third level of that SMU table. Now we've made a setter. So now we can set v, and we'll go it back to 0.5. There. Now we've set that voltage again. For make getter, going to be very similar. We can't use that function. We can't use that set voltage to get the voltage back though, because it's accomplishing the task of setting. So we need a new function to actually get that voltage back. And make getter is structured the same way, comma level v. Now we can do print get v. Again, these are ways to speed up your code, but they're only really beneficial if you're doing changing an attribute quite a bit, because there's a little bit of an overhead if you're talking about just raw speed to actually make those getters and setters. Okay, I think that's enough of talking to the instrument via console. Let's go now and start actually making a basic script. So we're going to switch up to using this editor up here. I will drag this down a little bit so that that's not taking up as much space. I'm going to go up to that new icon up there, use the wizard under Keithley, and I'm going to make a new TSP file. You don't want to make a just straight file or any of these, because the TSP file will give you some syntax highlighting, and test script builder will be able to help you find errors and things if you select this TSP file there. And I'm going to name this one diode test, because that's what we will actually be performing here. Now I've got my new script. So scripts overall can function very similar to just writing in the console directly. That's one way to use them. So for example, we can do print local node dot description. I'll use that again. I'm gonna, well, I won't quite save it yet because I want to show you something. I'm gonna right click and run editor contents. Now we'll see there, it printed that local node dot description. Now there is this run button up here. It's in some ways just accomplishes the same thing, but an important distinction there. If I click run right now, nothing happens. It doesn't look like our code actually printed anything, or it didn't do anything at all. And in fact, it didn't, because what we sent it in actuality was a blank file. The run button runs the last saved version of your file up here. Right-clicking and running the editor contents runs with whatever's live in the editor right now, whatever changes you've made. So now I'll just click Control S to save this, click the run button now. There we get our code behaves like we thought it would. You can also get to that run button by right-clicking underneath Run Editor Contents. There's this Run As. You can click Run As one TSP file. So that's also a way just to run the last saved version. But keep that in mind, because sometimes you may be tricked out if you don't save your files all the time. So let's try making a function here to perform a diode test. And this function will be then saved on the instrument so that we can call it back. We're going to measure the forward voltage of this diode that I have connected here. Functions have to end with end, so I always like to put that in at the beginning, and I'm just going to tab over so that it's a little bit more readable here. I'm going to start with a reset of the instrument in this function. I don't want any settings carrying over. We'll set some things here. We're going to set the source function to output DC amps, because we're going to be sourcing a current to measure the forward voltage. We're going to set the level to maybe 0.2. I wonder if I have that diode connected backwards, actually. I'll may have to check that. Of course, since it's an SMU, I can just set it to negative voltage. Oops. And I want source level I. There we go. Can't forget that, otherwise the instrument doesn't know whether you're trying to set the voltage or the current setting. And we'll do source.output equals SMUA. Output on. Try and keep it a little readable. Let's make a variable here, v smua.measure.v. And then we'll print that voltage back to the console. That's all we want to do right now. So I will save this, and I'll click the run button. Let's see what we get. And Nothing. Why did nothing happen? Well, because we defined a function, but we didn't actually tell the instrument to execute anything right now. So what we've done is we've created a new function here called measFvolt. So we can verify that. If we print that out, you can see we got our nice new function there. So now let's actually use it. Ah, there's that LED lighting up. And it's actually staying on, and it's brighter than I meant it to be. Dot source, output, and we'll just quickly turn that output back off again. Let's set this, 200 milliamps, of course. Let's change that back to say, maybe 10 milliamps. That'll be fine. Bright enough to be able to see there. So there, now we have a nice new test. Of course, if I want to change that value in what's actually on the instruments, I'll run the editor contents there. Now I've replaced that measFvolt function actually on the instrument. Important to know that just changing it here, remember, the instrument console is executing on the instrument, not on the computer. So if you change things in the editor, doesn't change anything until you actually run it, which sends it over to the instrument. So let's see how that looks now. There, that's a much nicer little green LED that we got going there. Oh, and oh dear, I got that wrong too. SMU.source.v. Oh, no wonder I was getting a runtime error. Measure.v. There we go. Let's resend that over to the editor contents. And try that now. There we go. Now we get our forward voltage coming back at about 3 volts. So let's make a couple changes to this now. We'll make it a little bit more advanced. Let's say instead of just being always set to this I level, let's make it a little bit more customizable. So let's try adding an input here. I bias, if I can type. There we go. And we'll change what this setting to I bias. Save that. We'll just run the editor contents. Now, let's do 0.02, maybe 20 milliamps. There we go. A little bit brighter, slightly higher forward voltage. This does run into a problem, though. If we do something like this and we don't supply I bias, you see we get a data type error. What we just tried to do, if you look at our function, we didn't supply I bias, so therefore it was nil. It didn't exist at all, so we tried to set the current level to something non-existent. So obviously the instrument isn't really able to process that. There's some quick ways to be able to fix that, though, that I like to use in a lot of my functions, and we can just easily set a default value. So let's say if not I bias, then I bias equals 0.01 and end. So this is just one line. You can make it a little bit more readable if we want. The line endings don't really have an effect. But so now we've said if I bias doesn't exist, then we'll set it to a default value. That's a quick and easy way to make sure that you don't wind up accidentally passing an error onto the instrument. And so now I'll resend this to the instrument and just prove that out. There we go. So briefly, a couple things about logic. We do have quite the logic that you'd expect in an instrument, which are really handy to perform complex tests. So, you can do things, you get true and false coming back from things. You can print not false here. This does mean, too, that true and false in some of these are reserved words, too. So you couldn't, for example, set a variable. You couldn't name a variable true. You could set a variable equal to true, though. So let's do t equals true there, and we'll do f equals false. And a couple key ones that are good to use is, let's say, t and or are our logical operators. So we'll print t and f, and we get false back. How and works is and will return the first variable if it's false. Otherwise, it will return the second variable or comparator. So if we do print, let's say, let's do something like 2 and f. Well, no, we'll do false and 3 something. That'll still return false. We'll do print 2 and 9, and we'll get 9 back because that first item, that first comparator 2, is true. Anything that's not nil or false is true in TSP, so that allows you to put numbers and things into these logical comparators, and if you want the return value, just keep in mind that it'll return the second if both are true. For or does the opposite. So if we do print, let's say, nil or true, it'll return true, or because it will try and return whatever's true. It will return the first item if it's true, or it will return the second. So if the second one is false, obviously, then you'll get false if you're comparing 2 false items. So to try that out, yeah, let's print 6 or false, for example, and that'll return us 6, just like we expect. Anyway, enough little bypass into logic. Let's go back into the script. So what we have right now is we're printing this value out to the console, but we're not really doing anything with it, and it isn't terribly usable if we want to use that forward voltage anywhere else. So one thing that we might like to do, that you might like to do in your programs, is we'll get a return value from that. So let's set V forward equal to measure F volt. You know, this is something that we'd like to be able to do. That won't work right now, though, because we haven't specified a return value. So let's do that. The keyword, very simple, return, and we'll just return that V value. I'm going to keep things printing out just for our reference. But that can be, now I'll save this, and we'll run the editor contents again, and let's try that again. V forward equals measure F volt. There, that's still printing, but now we can also just print V forward directly. And there we go, we got that same value again. So now we can use this, we could use this function now to do some really powerful things, since we're actually returning values onto there. Something else that we might want to do here too is, because this function is described as a forward voltage, we don't want to get a negative current in here, because that'll give us start giving us the reverse voltage. So let's use some more logic in here, some if logic, and we'll just say if I is less than 0, then we can just return and end. We're not going to return anything. So the function will return nil since we're not returning anything. But now, whenever the function will see that return, it will exit the function and just return whatever value you put here. So I could put, say, return false or something like that, depending on the logic that I want in the rest of my code or the rest of my script. So let's, now we have this, let's try playing around with showing off these readings on the instrument itself. Yeah, let's try putting some things onto the display. There is, of course, a display library that allows you to control what's going on in the instrument. So, for example, let's try display.screen, and we'll set it to display.smua, another constant there. Now we're looking at just SMUA of the instrument instead of that 2-channel setup. And we'll do display.clear if we want to clear off that instrument display and just get to a blank screen. We can reset the instrument too quickly. Now the output turns off, of course, and we go back to our blank. So that's one way. We can just have the instrument just put out that display on the front panel. So actually, let's set this up again. So one thing to note there is that while the output is on, that reading will stay there. SMUA dot. Let's turn that output off, and the reading will disappear. So maybe we'd like reading to stay up there a little bit longer. So what I'm going to do now is we're going to together, I should say, put together a little display of the user screen that we have on the 2600 models. So let's try that. I'm going to put some space in here. we're going to use the setText command, display.setText. And let's see, we're going to put the forward current that we're using. And there's an easy method for concatenating text and numbers together if you want to put things to the display or even just print them to the console. And it's just 2 periods. So we're going to do ... and we're going to use I bias. So now we're going to write out on the display if equals I bias. And let's also do the forward voltage as well. ... V. There we go. Let's try this out now. We'll run the editor contents again. Measure F volt. Oops, what am I comparing to? A output on attempt to compare nil to a number. Oh, I didn't provide it anything, of course. I'm just doing I there. That should be I bias. There we go. And that will also try and compare if we keep it there. So this should really appear after we make sure that we have at least some default. Otherwise, we'll keep on getting errors. Point out there is a debug mode in Test Script Builder. I'm not going to go into it today, but it's great to play around with if you come across errors that maybe are harder to solve than that quick one right there. Let's try this again. Measure F volt, and there you can see on the instrument display that we have that written out, but it looks a little bit truncated, right? We don't have very much. We got IF, VF is sort of trailing off the display, I think. I mean, there's more digits than that. So let's change this up a little bit. First, what we're going to do is after I bias, let's do a new line. The 2600s are 2-line displays, so a new line is $N, and we'll delete that space. We won't need that. So let's print the forward voltage, which is going to be a reading on the second line. We'll run that editor contents and measure that forward voltage. There we go. Of course, we do have, you notice that VF is still there, and that's because we wrote over what was there before. That's all we really accomplished. So we're going to put a display.clear in there as well, so that we can clear the display and rewrite it from scratch. But also notice in there that that's now way too many digits that we're getting for the forward voltage. I don't believe the instrument has a, however, that is like 16-digit resolution, though I don't know that that's even physically possible, come to think of it. So let's make that a little bit more realistic and maybe tone it down to just what we want. We're going to use the string.format command. And string.format follows the C conventions, the programming language C conventions for its printf, sprintf command. So there's some documentation in the manuals again, but in the Lua reference manual, actually, I think it's maybe a little light in our own reference manuals, but the Lua reference manuals can be pretty handy if you want to do some complex. I mean, or you can just Google the C sprintf command, and it supports all the typical ones. So now what this means is that we're going to use the engineering notation, little e, and we're going to use 1 digit. Actually, let's why not change it to 2 significant digits there. So we'll save that. Whoops. What's the error? Missing just notation. Oh, thanks, Test Script Builder, for catching that for us. Close that, go back to the console. Run editor contents. Measure F volt. There we go. And now we got something a little bit more reasonable there. So this has been just a quick overview. We're not quite done yet. We're going to go into a couple other examples, but here's just a very quick way to make a function. So now we've created that function, storing it on the box. To note, though, we haven't saved this onto the box yet. We're going to get to that later. In just a little bit. I've got a few things to show you in between there, but if we restarted the instrument, this measure f volt function wouldn't be there anymore. We haven't saved it to our non-volatile memory. Basically, it's just sitting in the volatile memory of the instrument. So let's do a maybe a little bit more complex example, and then we will keep everything nicely together. So I'm going to make make a new file here. We'll make a new TSP file. Keep it in that demo, and I'm going to change it out for the phet too. So I'm going to call this one phet test. Again, if you don't have a phet or an easy way to do 3 terminal tests, if you have a 1-channel instrument, that's fine. You can still get something out of watching this. I think for sure. So now what I'm going to do is I'm going to copy and paste some code in here, and then we'll walk through it. Okay, there's a little bit. What I've done is I've put 2 functions in this phet test here. So let's see what I did. And actually, well, I'm going to change this over to, I'll just reset the instrument actually to turn that output off, and I'm going to change it to a phet device that I have prepared. So what we're going to be doing with this next test is we're going to be measuring the on-state resistance of this little MOSFET that I have. So I'll plug this guy in fairly daintily if I can. And I'll pull over my second hidden triax cable that I have. This is going to be channel B of the 2600 that I have connected. And I'm going to connect the second output, SMU B, onto the gate of my phet. So now I'll be able to perform an RDS on test while biasing the gate. So let's look at that function that I've created here. We do see I've created a function measure RDS on. It's going to take a couple parameters here. Start voltage, a stop voltage, step, and a drain current, I drain as I've named it. So as you might guess, we're going to be sweeping from some gate voltage to another gate voltage, and we're able to define the step size. I've put in here a couple more checks. This time, maybe I don't want defaults, but I do want to not allow the test to proceed if I haven't provided one of these settings. So I'm just checking if not, and then in parentheses, any of these things. So remember how AND works. Is AND returns the first value if false, and otherwise it returns the second, but it's if not. So if all of these are true, then it will return a true value, and so not that nodding that true value will allow us then to come in here. So if any of these are false, basically, we'll go into this if statement. We can specify parameters, then just return. We've got some SMU configuration in here. These are all in the reference manual, so I won't spend too much time describing each of these. There is something to note here is that there's display.smua.measure.func. I'm using this attribute to set the measurement to ohms. So now we'll actually be able to display the ohms measurement on the front panel of the instrument. I won't be writing things out directly to the display manually right now. I'm also going to use the NV buffer, and we're going to start off by clearing that. NV buffer, each channel has 2 NV buffers built in. You can also make your own buffers, but buffers are where we store readings. NV buffers are just the default buffers that exist. They're NV because they are non-volatile, so they can persist through instrument resets. They don't do that by default, though. There's actually nvbuffer.save. There's a save command that will allow you to save those buffers should you wish them to persist through instrument reset. Do the exact same things for the B output, except we're going to be outputting DC volts, and we're going to be measuring DC volts. We won't actually be caring about the gate voltage, though, too much. Clearing that buffer. The test is pretty simple. I do have this tog output function here, so I'm using a function within a function. What does tog output do? It just toggles the output here. So I'm just checking if the output is on, then I'll turn them off. Otherwise, I'm going to turn the outputs on, just so that I don't have to have smua.source.output everywhere. Easier to just have that be a function, and I'm using it more than once. So, good functional programming practices. So we have a for loop going here, too. We're going to use the vBias variable that we'll define, and it's going to loop it's going to go through this for loop from our start voltage to our stop voltage in a step size. So anytime if you're defining a for loop, you have a index, and you can go from a start to a stop in a step size. I named them pretty easily, so that's shouldn't be too hard to understand. In a for loop, we're just going to do, and we're going to do these things here. SMUB, we're going to set the output level. The output's already going to be on to V bias. We're going to measure that voltage, save that to SMUB's default buffer, and we're going to measure the resistance. So SMUA is connected across the drain and source, so that'll be an easy way to check our, that'll be a measurement of our drain current. I'll point out here that turning the output on and then going through a loop here may not necessarily be best programming practices for if you want the most optimal speed of your instrument. I won't go into today how to get the most speed out of your instrument. That may be a different live stream topic. If you're interested in getting the most speed out of your instrument, click that link that's in the description and leave some comments. We'd love to hear from you. And in fact, if you'd like any other further topics on these live streams, then please do also use that link in the description and let us know, because this is something that we may like to do in the future. So let's save this. We'll send it over to the instrument. There we go. So now we've defined these two new functions. Again, nothing happened immediately because all this script was doing was defining the function. So let's actually try something. Mesh RDS on. And what values do I want here? I think we'll start at 0 to 5 volts in 500 millivolt steps and a drain current of 25 milliamps. This lines up somewhat closely with the specifications of the FET from its data sheet. So let's try that out. Now, nothing happened because we don't see anything because we're not printing any results. You can see that the display of the instrument changed, so you can see that that configuration happened, measuring ohms on channel A and volts on channel B. But let's print out one of those buffers. So we'll go from 1. Let's see, we're going to use the print buffer command, I should say. What print buffer does is it takes a start index, a stop index, and then a buffer. And it will just print out right here to the console, as you may expect. So let's go from 1. With this settings, this will give us 11 points, but there's an easier way. If we know we want to print the whole buffer, then we can do NV buffer 1, and we'll do .n. .n is a shortcut for the buffers that allows you to, it just returns the, or it is equal to the number of indices that are filled up in that buffer. So there's a different one. We could do capacity to see how many readings that buffer can hold, but n is equal to the number of readings in that buffer. So this is the stop index. We just want to read from that first index to whatever the last index is. And that is the buffer that we want to print out of. This will be the drain current. And we got our one reading back. SMUA, clear, NV buffer 1. Well, that's a reading. Print buffer, should be getting a few more than that based on how I defined things. Ooh, exceeds maximum reading. Okay, so I messed up something in there. Well, that is, so we do get more readings back here at the very least. I'll figure out what's up with that a little later, perhaps. But the other aspect of TSP that I want to focus on, printing the buffer is one thing. You can set this to return values of the buffer. You can perform math on the buffer later. So we'll let you play around with that a little bit more. But one thing I do want to do here is turn this into a pass-fail test. So as I mentioned, what we're trying to do is we're measuring the RDS on compared to the data sheet of the instrument. So let's turn this into a pass-fail test. So I'm going to copy and paste a couple more functions in here. So now I've got my measure RDS on function for actually measuring that through a sweep. We've got our tog output function. And, oops, we have our, where's our, tog output's down at the bottom. Oops, I pasted it in a little bit different from where I was expecting it to be. We've got our, a check RDS function. So we're going to be checking that resistance between drain and source with some parameter R max. I've set a default resistance, maximum resistance of 5 ohms here. And the check here is we want to check if the resistance exceeds this maximum resistance. We could iterate through in a loop the entire buffer and just keep on reading values and checking them individually against the maximum resistance. But there's a little bit of an easier way using the built-in buffer statistics capability. So I've created a variable here, statistics, set it equal to that SMU buffer dot get stats, and it takes as a parameter the buffer that you want to get the stats of. So NV buffer1 here. Then I'm going to print the maximum reading within that buffer. So statistics actually, that variable will contain a whole lot of different things. So for example, after I create it, won't return anything right now since I haven't done anything, but I can return, say, the mean of the entire buffer, all the different readings there. Or there's maximum, and maximum actually returns you get the maximum of a few different things, just all for free. So you see here we're trying to get maximum of reading. You can also, for example, get the maximum of the source values of what you've been sourcing out. So you'll get a couple different things. You'll get a couple different tests there that come along for free with statistics. So now instead of iterating through a loop, we're just going to do one statement. We're going to check if the maximum reading is greater than R max, then we'll return false. If not, we'll return true. Then there's another function, update the display. So now I'm going to actually write some things to the display. We'll get the return value of check RDS, and I'm just going to name it a variable pass here. We'll clear out the display. We're going to set the cursor so that whatever the text we display will appear. 9 is a little bit more in the middle of the display, as you'll see. Now, if it passes, then we'll set the text to pass on the display, and if not, we're going to set it to fail. So this update display also calls check RDS, so I'm going to add that update display function, to our earlier measure RDS on. So we'll save that, run it over to the instrument. Now let's try, well, you're able to just call measure RDS on. I'm just going to copy and paste the settings that I want in there. Start at 0 to 5, 500 millivolt steps, and an drain current of 250 milliamps. So let's see there. And we pass. That's good to see. Let me disconnect something so that we can make sure that it actually will fail properly. So I'll disconnect the drain high there. And let's run it again. Oops. Actually, I'll just paste the exact same things again. And there, you see over on the display, we get a fail now. So let me connect that high output up again. So this maybe is a nice test that we want to run remotely on this instrument. We may want to check a lot of these. These diodes and just make sure that you know, the maximum on resistance maybe never exceeds this value that we've set. So let's store this on the instrument itself so that we can run it remotely. The way to do that is we'll go up to this run button, not clicking the actual run button itself, but click the little drop down and run configurations. And this will open a wizard that may look a little complex, but I promise you it's not that bad. What you do is you select a project over here on the side. It auto-selected the demo script since that's what we're working in right now. And you see the different project files that we have in that demo project. So I'm going to add both of them over here to the loading of what we have, the load order of our script. And I'm also going to save this to our non-volatile memory over here under script attributes. Volatile means it'll be deleted when the instrument restarts. Non-volatile, we'll keep it along. I'm going to load both of them onto the instrument. So we'll just run that. Now it's sent demo script over to the instrument. Something else I want to do though. So again, that script, all it does is define these functions. It's going to define this function, and nothing over here because there aren't any functions, even though we sent it along. But it's not going to execute anything. So what I'm going to do is I'm going to make another script to make sure that something actually executes. And we can define a new script besides using the run configuration. You can also just type it down in the editor here. So I'm going to make a new script called run test script.new. Here's the code that I want to be there, and then I'm going to name the script run test. This is a variable name. This will be the saved name that we assign to it. So now I've defined that. I also want to save it to non-volatile memory, because right now it's just in volatile memory still, so I want to save it to non-volatile, so I'll do run test.save. Now it has created something, now it's created that script on the instrument, so I can verify that, run test.list here, and you can see that's actually what we have. This end script and load script, you see load script, run test, and then these end scripts. If you're, instead of using test script builder sort of handles this load script and end script automatically for you. If you're instead writing your scripts in something like Python or MATLAB or even C, any programming language, when you communicate with the instrument and you want to save a script, you'll use these load script and end script commands. Very simple, you just put the code in here and just make sure that they're bookended by this load script and end script. Again, test script builder though handles that for you, so you shouldn't use them when you're using test script builder. So now I'm going to restart the instrument, and we'll give it a second to start up here. And I just want to, last thing I want to do here is just prove to you that this will actually execute by itself, and also show you briefly how you can run these commands from the instrument front panel if you're not familiar with it. If you need an instrument to operate completely by itself without any computer control. So what I'm going to do is I'm going to go to load. I'll go over a little bit to scripts. First thing I'm going to load, I could configure this differently, but as I have it, I've got demo script as the functions. I'll click the run button there. Now it's loaded those functions. Again, it hasn't done anything though, so we'll go load. Enter into our scripts. I'm going to scroll over to my run test. There it is. Enter. Now that script's loaded, I can click the run button to actually execute it. And now we get a fail. I don't know, maybe the properties changed. But that is a little bit of a introduction to TSP and how to write your own scripts and your own programs onto TSP. So that's everything that I wanted to address today. I wanted to thank you all so much for attending. I hope you learned something or became familiar with TSP if you didn't know anything about it before. I do invite you to visit our GitHub, github.com/tektronics/Keithley. You can find lots more tutorial code for the 2600s if you want to become more familiar with your instrument. If you have more comments, questions, or need further technical help, be sure to click the link that's down in the description below so that we can follow up with you. And you can also subscribe to the Tektronics YouTube channel if you want the latest updates on our products and interesting industry information. Once again, thank you so much for attending, and good TSPing.